And
then welcome to the Winds and Currents webinar. Today, we're fortunate to have Amala Mahadevan, who's going to talk from Woods Hole Oceanographic, and she's going to talk about vertical transport and its biogeochemical implications. So thanks for being here. I'll let you go ahead and start sharing.
Okay, yep. Thank you very much for having me, Sarah. Let me see, I think there's a way for me to get rid of this control panel. Do you see my control panel or?
No, looks great.
Oh, it looks great. Okay, great. Okay, so I wanted to talk about vertical transport today because I think that as we start getting to higher and higher resolution observations of the sea surface, one of the questions that people are asking is whether we can figure out what the vertical velocities are in the ocean. But I want to stress that, you know, it's not just vertical velocities. We are interested in what their implications are. And I want to say that vertical velocities have a really outsized impact on the biology, right? So why is the biology in the ocean or phytoplankton in the ocean so sensitive to vertical velocity? And it's because phytoplankton needs light and nutrients. And light is at the surface or coming from the surface, decaying exponentially with depth roughly, and nutrients are deep down below. And these nutrients need to come up into the surface layer where there's light for production. So the phytoplankton productivity, as we see from space, is very uneven in space and time. We see big seasonal blooms in the subpolar gyres. The subtropical gyres look relatively low in chlorophyll, but we are missing a lot by looking only at the surface in the subtropical gyres. And these vertical motions really affect the biogeochemistry because of the very, very strong vertical gradients in properties. So if you look at the nutrient profile, for example, in the ocean, it's lots of nutrients at depth. So pretty much any property profile that you look at the ocean, the gradients are very strong in the vertical. And the gradients are very strong in the vertical because the ocean is not well mixed vertically. And that also means that if you intermittently or sporadically bring some water up or bring some water down, then it's going to have an effect. For example, if you bring up some water, then it has nutrient rich, you bring it into light, then you expect there's some biological response to it. So I want to start by acknowledging that these vertical motions occur on multiple space and time scales. All of these are important and they all come together in some way, but I am going to focus today on talking about this range of scales, you know, sub-mesoscale to mesoscale, because these range of scales are very well strongly coupled with the biological scales or the biological time scales. So when the time scales of the physics and the biology are very strongly coupled or similar, then you see a response, which is, I would say, in a way that you can see the response and the fluxes are enhanced. So the property fluxes or the changes or the growth rates are enhanced. And I'll show that a little later in this talk. Okay, the larger scale motions are also important. They kind of replenish the reservoirs. For example, you can have to replenish the nutrient reservoirs, you have to replenish. And I want to say that horizontal and vertical motion in some sense really go together, right? So the horizontal motion is redistributing things on isopycnals and stirring things around. And in these pictures that you see of surface chlorophyll, it's not just vertical, it's the horizontal always dominates the horizontal velocities. But somewhere things are moving vertically to sustain this productivity. Okay, so what is the difficulty with measuring vertical velocity? One is that it's very, very small compared to the horizontal velocity. And you can see that just by looking at the equations of motion and non-dimensionalizing them. So things are more or less in geostrophic balance. That's your horizontal velocity, more or less in hydrostatic balance. And if I think of my Rossby number, typically at mesoscales and large scales, the Rossby number is much smaller than 1. And the aspect ratio, which you can think of as a ratio of depth to length scale, is much less than 1, so which makes the ocean more or less in hydrostatic balance. So how large is the vertical velocity? And you can look at that by saying that the ocean is nearly incompressible. So the flow is divergence free. And down here, you can see that if you try to scale what the vertical velocity is, it would be, in my opinion, quite wrong to say that W over D, that vertical gradient of the vertical velocity, is as large as U over L, because these two terms, du dx and dv dy, almost cancel each other out in the ocean. So in fact, dw dz is much smaller than than U over L, right? W over D is much smaller than U over L. And you can, by scaling the vorticity equation, try to find what the size of W is. And it turns out that, of course, you expect it to be the aspect ratio times U, but there's also a Rossby number in front of it. So at large scales, when the Rossby number is small, then you expect the vertical velocity not only to be delta times U, the aspect ratio times U, but the Rossby number times the aspect ratio times U, okay? So at large scales, the vertical velocity is particularly small. So what happens? Why are we interested in submesoscales? Okay, so firstly, I want to say that we are interested in vertical velocity. I'll tell you why we're interested in submesoscales, because the Rossby number is order 1 at submesoscales. And we are thinking about vertical transport, or that's what we're interested in for the biology. But making the connection between velocity and transport is non-trivial. So firstly, vertical velocity is difficult to model and measure. It's difficult to model because the equations are highly skewed. So you have the horizontal momentum equations. And in fact, if you make the hydrostatic approximation, you have no equation for the vertical velocity. So you're getting it from the horizontal divergence. And when you look at the horizontal divergence, then it nearly cancels out. So a small error that you make, if you make a 10% error in calculating the horizontal divergence, you get a huge error in the vertical velocity. So calculating the vertical velocity, even in a model, is non-trivial, and the models are highly sensitive to any changes. So if you try to compare the solution and you make slight changes in the model or perturb the model, you get very different vertical velocity fields. So in some sense, from a modeling standpoint, I think that instantaneous vertical velocities are really difficult, but I hope that with time we can get some sense of the integrated transport, because the vertical velocity field, of course, also has internal waves in it and a lot of high frequency stuff, and the motion of the isopycnal, some of which is reversible. So you have to think about what exactly you're trying to say when you want the vertical velocity. The other thing is that the spectrum of the vertical velocity or the vertical kinetic energy is much whiter than that of the horizontal kinetic energy. And so that means that the small scales are really important, and I'll show that, okay? So the vertical transport itself, we want to get to vertical transport, and it depends also on the distribution of the properties. So there's vertical velocity. Now we want to get to transport. It depends on the distribution of, for example, nutrients. If you're thinking of how nutrients are brought to the surface, then the concentration of those properties also depends on the sources and sinks of those properties. So we need to know, of course, some sort of background or mean concentration. But if you think about what the concentration is because of some flux, like if you think of W times N, where N is the nutrient or your nutrient anomaly, then now the nutrient distribution or the nutrient anomaly depends on the sources and sinks for the nutrient or the uptake timescales. So it's linked again to the biology, or the sources and sinks are the biological timescales. So I'll talk a little bit about that. Okay, so why I just mentioned that the vertical velocity spectrum is whiter than the horizontal kinetic energy spectrum, and submesoscales are very important. So what I mean by submesoscales are motions where the Rossby number and Richardson number is order 1. Okay, so as I just said, the vertical velocity scales like the Rossby number times the aspect ratio times U. And so when the Rossby number is order 1, then you get enhanced vertical velocities. And this happens spontaneously at fronts through frontogenesis. And so if you look at a front like this, it's in the ocean, which I've tried to depict. Then at the surface, fronts intensify. And so even though buoyancy, so I'm referring to B as the buoyancy, just think of it as the inverse of density. The buoyancy is conserved moving in the flow, even if there's no warming or if there's no cooling or no change in the density. But the horizontal gradients of buoyancy are not conserved. And so the terms on the right-hand side of this equation, if I think of d by dt of the horizontal gradient of the buoyancy, so y being in the cross-front direction, then I get these terms on the right-hand side, which are the frontogenetic terms. So as a front becomes unstable because of baroclinic instability, you spontaneously get this intensification of the horizontal buoyancy gradient. And your front, the isopycnals are squeezed together in some places, frontogenesis, as you call it, and they're spread apart in other places of frontolysis. So where the front dB dy, or the lateral buoyancy gradient, increases because of the spontaneous frontogenesis, then the flow tries to come back into geostrophic and thermal wind balance. The jet intensifies there, and the jet intensifying means you get vorticity on both sides of the jet, positive on one side and negative on one side. So you have positive vorticity on the dense side of the front and negative on the light side of the front. The vorticity intensifies. And when the vorticity intensifies locally, the vorticity becomes as large as the planetary vorticity F, and you get Rossby number order 1. Rossby number order 1, it means that the geostrophic constraints not so large or strong, and you get a secondary circulation at the front with upwelling on the warmer side and downwelling on the colder side. And so that's what we think, that's why we think that these submesoscale dynamics, where locally the Rossby number becomes order 1, are really important. And what we found is that as you increase the resolution of the models, you see this happening everywhere in the ocean. So while we've been looking at the eddy field using sea surface height, it's hard to see this asymmetry. There's an asymmetry. The positive vorticity increases more than the negative vorticity. I'll show you that in a second. But that's difficult to see from our current methods of observing the sea surface height. Okay, so submesoscale processes, I'm going to say they impact phytoplankton growth in multiple ways. The vertical motions at fronts is really enhanced. And so you might have a front like this, and you enhance the vertical supply of nutrient at the front. But you can also get a vertical motion, which is a reorganization of buoyancy, which leads to the re-stratification of fronts in the mixed layer. So in places where you have deep mixed layers, the re-stratification of buoyancy or the reorganization of buoyancy in an adiabatic sense causes lighter water to move over denser water, re-stratifying the front and changing the depth of the mixed layer. So because phytoplankton are responding both to light and nutrients, both of these scenarios can be important. So the first one, we think of it as being more important in subtropical gyres. And subtropical gyres, this red line is showing us a typical density profile. The depth of the mixed layer is very shallow. And the depth to which the light penetrates the euphoric layer tends to be deeper than the mixed layer. And I'm going to just term those places as subtropical gyres, or where this dynamics of vertical motion is important, because if you look at a nutrient profile, then we find that nutrient is depleted to a depth below the mixed layer. And so the nutricline is deeper than the mixed layer depth. And so the uplift or the upward transport of nutrients into this layer, even below the mixed layer, is where you see a lot of the productivity occurring, and it's missed from satellites. We are really interested in knowing what those rates of productivity are. And to know those rates of productivity, we'd like to know how much nutrient is lifted up into this euphoric layer, which might be below the mixed layer. And the subpolar gyres, for example, this light really matters for phytoplankton. The mixed layers are very deep, and so you might have a mixed layer which extends to much deeper than the depth to which the light penetrates. And that's also because the sun angle is very low in the subpolar gyres. And so the mixed layer being very deep, you have plenty of nutrients in the mixed layer here. You have plenty of nutrients in the mixed layer, but the productivity is limited by light. And so this sort of re-stratification of the mixed layer by mixed layer eddies and submesoscale processes means that you shallow the mixed layer by eddies, and that shallowing of the mixed layer means there's more light confined to the mixed layer, and you get these phytoplankton blooms. Okay, so these are two ways in which these submesoscale dynamics really affect the biogeochemistry: the vertical transport of nutrients, the vertical transport of carbon, oxygen. Carbon is exported from the surface, we think, by submesoscale processes. And the other way is the vertical transport of buoyancy, which rearranges or reorganizes the structure of the mixed layer. Okay, so if anybody has questions, feel free to ask them. I'll just keep going unless someone stops me, but yeah, happy to address along the way. Okay, so earlier I said, a couple of slides ago, I said that fronts spontaneously intensify in the mixed layer, and I'm showing you here a numerical simulation of a front. I initialized, this is a periodic channel in the east-west direction, and in the north-south direction, there's solid walls, and the channel is like 300 and something kilometers in the north-south direction and 196 kilometers in the east-west direction. And I initialized it with a section which was observed in the ocean, and I let it go, okay? So this was an observation of a section from the Bay of Bengal, and I'm looking at surface salinity, surface temperature. Here, the fronts are very much controlled by salinity. And what you see here is the vorticity field at the right. And probably the thing that really pops out here is the filamentous nature of the positive vorticity, right? So this is one of the characteristics of submesoscale dynamics. The fronts intensify. Positive vorticity tends to be a much larger in magnitude than the negative vorticity. And one simple argument that you can provide for that is that, it can be much larger than F, but the negative vorticity doesn't get much smaller than minus F. So that you see a greater dominance of positive vorticity. And if you try to look at the statistics of these fields, then the vorticity is shown here on the left and the vertical velocity on the right. And so you can see a PDF of the vorticity. It's highly skewed. You see much larger values of positive vorticity. And you see locally, if you measure the Rossby number as the relative vorticity to the planetary vorticity, you can see that the Rossby number is order 1, or in many cases, it's much larger than 1. And that occurs in these very narrow filaments, which are essentially fronts. If you look at the vertical velocity field, what you see from the PDF of the vertical velocity is that the downward motion is much more concentrated and intense than the upward motion. Okay, and so if you think about a front, it was downwelling on the side of positive vorticity. I'll show you that again in a couple of slides, and upwelling on the negative vorticity side. And so you see this downwelling as much stronger than the upwelling along these filaments or fronts. And that has implications too for biology. There's an asymmetry in the up and down, and you can see the downwelling very nicely in tracers. I'll show you some observations very soon. Okay, so we can try to look particularly with the downwelling, we can look at the downwelling pathways. And those are much clearer than the upwelling pathways because we can really put tracers or particles in the surface ocean in these models. And we can also use natural tracers in the ocean to look at downwelling pathways. The downwelling tends to be more intense, more concentrated, and more coherent than the upwelling. And so this is a model simulation in which you're seeing red and blue is showing the vertical velocities. Red is upward, blue is downward. Downwelling is stronger than upwelling. And if I look in the model on an isopycnal surface, so this motion that we're looking at is largely adiabatic on isopycnal surfaces. And we seeded the model. This was done by my student, Mara Freilich, seeded the model with particles and the surface layer and watched where the particles go down. And the particles go down along these isopycnal surfaces. They go down where you have this very strong positive vorticity, and they go down on a time scale of a few days, okay? So now we can look and see where those particles went down along the front. And this is showing you a surface snapshot of the front on day 46, 51, 56, so 5 days apart. The black lines are contours of density, a horizontal slice through this close to the surface, and the dots are the particles that are colored because they're going down. Okay, so Samara colored only the particles that are subducting from the surface mixed layer and leaving from the base of the mixed layer into the stratified pycnocline. The color on these dots here is the color of the vorticity. And so one thing that you could notice is, like we were saying, frontogenesis leads to downwelling on the dense side of the front. You can see in these particles that almost all the particles that are subducting, especially except for a few here, are positive in their vorticity. So positive vorticity, water parcels are subducting. And so it's strongest on the dense side of the front with positive vorticity. And now what you can do is that you can do Lagrangian analysis, so as I was saying, is that frontogenesis is occurring, it's intensifying the fronts, that's causing a secondary circulation. But one of the difficulties in studying upwelling and downwelling is that vertical velocities are much weaker than the horizontal velocities. So as something is going down here, it's really zipping along the front with a horizontal velocity that is 1,000 or 10,000 times faster than the vertical velocity. And so looking at Eulerian fields is very difficult to identify frontogenesis. And so what my student Mara did is she tagged every one of these parcels, water parcels, and calculated on them. And on those water parcels, the time that they subduct or leave the mixed layer is time 0. And then composited all the water parcels. And we're looking at n squared, which is the stratification normalized by f squared in green. So the water parcels are in the mixed layer where the stratification is low, and then they subduct out of the mixed layer at time 0 and enter the pycnocline where the stratification is high. Okay. Now you can also look at m squared. So m squared is the horizontal dense buoyancy gradient. And so you can see that the time that the water parcels subduct, that's the orange line, the horizontal buoyancy gradient increases and then it decreases again. So the subduction occurs at the region of the strongest buoyancy gradient, positive vorticity, and they go from an unstratified mixed layer into the stratified pycnocline. Similarly, you can look at the vertical velocity and the vorticity on these particles, and you can see that the vorticity increases as the particles come into the fronts. And as they come into the fronts, that's the region of strongest positive vorticity, and then it decreases as they subduct out of the mixed layer, and the vertical velocity increases as it comes to the front. Okay, so what's important to remember is that, so if we think that frontogenesis is one of the dominant mechanisms at submesoscales that are moving things out of the mixed layer into the pycnocline, and vice versa, it's harder to track the upwelling because it's occurring from many places in the interior. We can track the downwelling more easily. And the downwelling occurs in a small fraction of the domain. So that's occurring in a very, I would like to say that these pathways of subduction are more or less coherent. Like if I say what fraction of the surface area in which water parcels are subducting, even though they were seeded everywhere, it's a small fraction of the area. Okay, so that's a little bit for the mechanism. And now we can see, can we actually see this in observations? So to the left, I'm showing you a model simulation now with tracer in it. So the surface of the model, so the surface mixed layer of the model, we added this tracer. This tracer is green, so think of it as phytoplankton or chlorophyll. And we wanted to see where it subducts out of the mixed layer. And this was motivated by the fact that if you go in the field and you look at chlorophyll, for example, so this is a front that we surveyed here in this red line. It's in the Western Mediterranean and the Alboran Sea, this little red line here. And this is a cross-frontal transect. So we have dense water on this side and this lighter water on this side of the front. And we've made measurements by towing a CTD, tow-yoing a CTD with an eco-puck behind the ship. This is chlorophyll, and this is depth down to 200 meters. And this is longitude, so this is going across the front. And so you see that you have high chlorophyll subsurface here. So this is what you might call the chlorophyll maximum at a depth of 45 meters. And you can see that some of this chlorophyll is going to get being subducted along these isopycnals. And you can see that very clearly here in the backscatter. So BBP is the particle backscatter or optical backscatter, in which you can see a plume of small particles being subducted along this front. Okay? So that's a 2D view across the front. But as I was saying, you have to remember that the flow is coming into the page. So it's going really, the frontal flow is going into the page. So everything is moving along front much faster than across front and downward. So when we look at these tracers in the model, one of the peculiar things that we see is that these tracers are subducted, but you get these regions of a subsurface maximum. So if I were to take a vertical profile at this point, I hope you can see my mouse, then you would see high chlorophyll in the surface, then you would see low chlorophyll in this vertical profile, and you would see a secondary maximum in the chlorophyll subsurface. And if that secondary maximum occurs below the euphoric layer, what it's telling us is that secondary maximum chlorophyll could not have been mixed from the surface, because now the profile is non-monotonic, and we expect the highest chlorophyll to be in the euphoric layer. So a non-monotonic vertical profile in chlorophyll tells us that there's a secondary maximum which is not related to growth, and it must be due to the vertical transport or subduction, which is now linked with the horizontal transport. So if I think about this feature here, the subduction, what I'm seeing here of the tracer, is probably subducted somewhere way upstream of it, and then it's coming along with the flow and getting subducted. Okay, so along isopycnal transport of chlorophyll, we think we can see this in observations, but the pathways are more three-dimensional than we can actually easily tell from the observations. So recently we were in the Mediterranean Sea, and we tried to track down this sort of three-dimensional motion using chlorophyll and oxygen as tracers. This is an eddy here that we surveyed. It showed up as high chlorophyll here in the satellite data. And we made several ship transects over that eddy, okay? And this curtain plots are showing you vertical profiles. These vertical profiles are made by toyoing something below the ship, and we could measure temperature, salinity, oxygen, chlorophyll, and backscatter as we are toyoing this instrument. So each one of these dots is a vertical profile. The X and Y axes are latitude and longitude. So latitude on this axis, longitude on this axis. And we are toyoing, dropping these instruments to a depth of about 200 or 250 meters, okay? So what you see here is the density, or salinity was really dictating density. So the salinity shows up as a dome. So we were trying to survey this eddy. It's a cyclonic eddy, shows up in a dome of high density subsurface or high salinity subsurface. At the top of that eddy, we saw very high or enhanced chlorophyll. And what we could see along these sloping sides of the eddy is that some of that chlorophyll is being subducted. For example, here you see one of these subducted features. Here you see another one. And you can also see them in oxygen. So oxygen is high, again, in the surface mixed layer. It's supersaturated because of chlorophyll, but at the sides or along the flanks of these eddies, you can see these intrusions or subducting features. So this is an example of how vertical velocities are affecting the transport of biogeochemical tracers, chlorophyll, oxygen, but very, very important to remember that these things are happening in 3D. So the horizontal flow field is much larger than the vertical flow field. Okay, we're at nearly at the half-hour mark, so I'm going to maybe cut some of my slides, but let me talk about this two kinds of vertical motion. So right now I talked about things moving along isopycnal surfaces at fronts, but there's also the uplift of the isopycnals. So as things are moving along the fronts, isopycnals themselves are going up and down. And if you have a nutrient, for example, and you bring it up into the light, for example, in a mesoscale eddy, as uplifting nutrients into the light, then you expect also to see a biological response. So we tried to separate these two kinds of vertical motion. One is the up and down motion of the isopycnal, which I'm calling W uplift. And the other is the vertical velocity that's along sloping isopycnals, the vertical component of that, which I'm going to call W iso. And the reason to do this is because we wanted to see whether there's some difference in this when you intensify fronts, for example, is one larger than the other, okay? So to do this decomposition, we have to be in the Lagrangian frame, because if I'm in the Eulerian frame and I'm trying to measure W uplift at one location and an eddy comes past this location, I would see the isopycnals going up and down. But for a water parcel and an eddy, for the most part, the water parcel is just going round and round the eddy, right? And so it may not be going up or down, and I don't want to calculate that as vertical motion. So we took the horizontal velocity field. This is, again, work done with Mara Freilich, my student. We took the horizontal velocity field and we decomposed it into the rotational and divergent part. The rotational part is the dominant part, and we tried to look in the Lagrangian frame of the rotational velocities. So we took the divergent velocity and projected it on an isopycnal. That's this black surface. We took the vertical velocity projected on the isopycnal and then calculated the vertical component of that. So that gives you an along isopycnal vertical velocity. Okay. And this vertical velocity scales, as I said, is the Rossby number times the aspect ratio times U, the total vertical velocity. But now in a model, we can decompose the vertical velocity as the along isopycnal part and the isopycnals going up and down. And we did that for a numerical model in which we use different resolutions. And we also changed the intensity of the fronts. So this delta T is 2, 3, and 4 degrees, telling you what the total temperature contrast is across the domain of the model. So delta T is 4 degrees, has very strong fronts. Delta T is 2 degrees, has weaker fronts. And we ran the model at 2 different resolutions. And we can decompose this vertical velocity into now this uplift and a long isopycnal vertical velocity. And when we look at it on an isopycnal, it's all done on an isopycnal. It's very difficult to tell what's happening, but we can do something with the statistics of that. Okay. So the uplifted part is the dotted, and the solid lines are the isopycnal part. And what this is showing is, let's just look at the red lines are the weaker fronts and the green lines are the stronger fronts. Let's forget the blue line for now. Okay, so this is showing you a spectrum of the vertical kinetic energy, you can say. And what you noticed is that the spectrum is somewhat red. It's much flatter than the horizontal kinetic energy spectrum. And if you look at weak fronts, what you find is that there is more energy in the motion of the isopycnals. So the vertical velocity associated with the isopycnals at mesoscales, at large scales, is much larger. But as you come down to smaller scales, then there isn't as much of a difference between the along isopycnal part and the motion of the isopycnals. And when you look at strong fronts, then you find the total vertical velocity, the more energy in the vertical velocity, but the motion of the isopycnals and the along isopycnal part is about equivalent at small scales. So this kind of helps to resolve some of those questions that people have been asking about for a long time. Is it isopycnal uplift or is it along isopycnal transport that really affects biology? And what this tells us is that we are missing in coarse resolution model, we're missing this part, and this part it's the along isopycnal velocities which are more sensitive to resolution. Okay, and you can see that when we compare the coarse and the fine resolution models. So something else that we can see is that we can also look at the PDF of the vertical velocity, or the PDF. In this case, we added nutrient to the model. So if you look at an isopycnal surface, this is in the euphoric layer. The nutrient is stirred on an isopycnal surface. The isopycnals are also moving up and down, and it's also climbing the isopycnal surface and being consumed. And at the strongest fronts, which are the green lines, at 2 different resolutions, what you see is that the highest fluxes, or the strongest fluxes, are really in the tails of this distribution, where you get the very high fluxes. And the 1 kilometer model resolution has much fatter tails than the 4 kilometer model resolution. And you see that the stronger fronts, which are the green lines, have much fatter tails than the weaker fronts, which are the red lines. Okay, so what this means is that resolution, or model resolution, really matters for resolving the vertical fluxes. The highest vertical fluxes, or the extreme values of the fluxes, occur, which are the tails of the distribution. And we want to see how fat the tails of these distributions are. And the tails are fatter for stronger fronts and finer model resolution. Okay, so I think I'm sort of reached the end of my time. I'm going to just go to the conclusions, maybe, if that's okay. Sorry. And say that vertical velocities, have a very large range of scales, but the submesoscale timescales of a few days are very strongly linked with the biological timescales, and you see a strong response for coupling with them. And the along isopycnal vertical velocities are more sensitive to model resolution. At large scales, the uplift dominates, uplift dominates definitely, but at sub-mesoscales, the along isopycnal transport, which we can actually measure or see in the field, is starts to show up as being very important. So the other part, which I didn't talk too much about, is that the nutrient flux depends not only on the vertical velocity, but also on the phytoplankton growth rate, because you have to think about how these things are coupled. So if you don't remove the nutrient as it's fluxed up into the euphoric layer, then you would get rid of those gradients. So the faster you remove it, then you have a stronger gradient. But if you remove it too fast, then in fact, you don't have a nutrient anomaly. So there's an optimal time scale for the consumption of the nutrient that maximizes the flux. And that time scale is in fact when these two time scales are matched. So I'll leave on that note that, maybe it's not a coincidence that the growth rates of the phytoplankton are in the range of, days. So on the time scale of 1 to 10 days, there's a wide range in the phytoplankton growth rates. And maybe that has something to do with the ocean physics, and that's how phytoplankton are evolved to take advantage of those physics. Okay, I'll stop there and let me know if I should stop sharing at this point. I'm happy to take some questions.
Yeah, thank you very much. This is great. Are there questions for Amala? Maybe
Hi,
while
Amala.
people, oh, go ahead.
I have a comment and I have a question.
Sure.
For you. So firstly, I just wanted to make a comment because we saw a very interesting talk that relates to your talk by Tom Farrar a couple of seminars ago, maybe. And there he was showing some measurements of these very strong cyclonic filaments, which I think are, if I remember correctly, it was just a while ago, very strongly correlated with a strong front in temperature. I think this was the recent SWOT measurements. And yeah. Tom, please correct me if I'm wrong. One comment that I wanted to make was that when you see these downwelling portions at cyclonic filaments, as they go down, it requires a crossover. In other words, it requires a crossover of material from one side of the front to the other. You almost never see the downwelling happening such that it moves away from the front. And the reason for that, I think, relies on the conservation of PV. Because if you think about the material near the surface having low PV, then as it gets closer and closer to the front, pinched by the frontogenesis, it's going to lower the PV even further because BX term, the horizontal terms are getting larger. And so therefore it has to acquire more and more cyclonic vorticity to keep the PV the same as it was when it was further away from the front. And then as it gets close to the front then and begins to get subducted, now finally it reaches a state where the horizontal terms are again small. So in order to conserve PV, it must acquire some anticyclonic vorticity. In other words, it has to go from the cyclonic side of the front to the anticyclonic side of the front once it's subducted. And so that's one of the reasons why you see the subduction happening from the cyclonic side to the anticyclonic side and almost never from cyclonic side away from the front. That's a comment. The question I have is, you showed a very nice part towards the end of the talk where the isopycnal, W isopycnal becomes more and more important as you go towards submesoscales and finer resolution models. From my first comment, and from what you showed earlier in the talk, we know that the downwelling velocities are strongly correlated with the cyclonic vorticity at submesoscales. Do you think the W iso has a relationship with the vorticity at submesoscales as well? In other words, we know that the down part of W iso may be related to the strong cyclonic vorticity. Do you think the W isopycnal up, which is what you're showing in the last few slides, does that have a relationship with the vorticity distribution as well, or in particular with the anticyclonic side of the front?
So yes, so you see the secondary circulation at fronts, and the secondary circulation is tilted with the positive vorticity side going down. It's much harder for me to say something conclusively about the upwelling because tagging those water parcels. So we haven't done that same kind of Lagrangian analysis that Mara did with the cyclonic, with the downwelling or the subduction, because we can put a lot of particles close to this in the surface mixed layer and watch them subduct, whereas the upwelling occurs from several depths. So we need to see the interior, and it's like the analysis is more difficult. But yes, I do think that the upwelling is going to occur on the anticyclonic side. It's going to be less coherent and less strong, the vorticity, as it occurs. So it's going to be also not as distinct as we saw it here. We think that the downwelling is particularly coherent and associated with a very strong cyclonic vorticity, which is skewed. Yeah. And then the downwelling, the vertical velocity is also skewed. So for all those reasons, we think that there's a much more coherent pathway downward than upward.
Right. And for the downward pathway, can you comment on the horizontal? Do you always see it going over, sort of crossing over from the
Yeah, we
lens
see it
side
going
of
into the
towards the lighter
stratified
side?
pycnocline, and it's going along the isopycnals into the stratified pycnocline. So it is crossing over, and you can increase the PV by both, or change the PV as following the water parcels also by changing the stratification. So it's going, from unstratified region into the stratified region, but the PV also depends on the n squared. Yeah.
Right, but it has to acquire the negative zeta in order for it to conserve, because it has the Fn squared, so it has to get the negative zeta n squared.
Yes,
unless
correct.
some
I think
curvature
that's
effect or something else.
Yeah, I agree with that. Maybe we should be following what happens to the vorticity on the particles. I suppose we could do
That's
that.
what that was one of my follow-up was.
Okay,
have you tagged those same parcels, Lagrangian parcels, with PV? And it may not be exactly conserved, because that depends on how you're forcing the model and what the mixing and model is doing as well. But
it's sort of conserved the PV.
Right.
Yeah, it's very hard to calculate, because it involves a lot of gradients, and then gradients on the Lagrangian particles. So we don't have like full confidence in showing it, but I think you're right. Yeah, we could certainly plot the end vorticity on the particles.
Right. Thanks.
Yeah. Good point.
Thank you. Are there other questions? Maybe I'll ask, I see that there's a question from Jake Winograd. Do you want to go ahead?
Hi, Amala. Really nice talk. Thank you. So I'll try to articulate this question. I don't know how well I'll do, but so I guess I understand how, if you have some sort of mesoscale strain field, which is frontogenetic, that could drive an along isopycnal transport. But then we also know that as you approach the submesoscale, the frontogenesis becomes dominated by the divergent field, and many of those dynamics, the sort of overturning circulation, is either closed in the boundary layer or just slightly below. And I guess conceptually, I'm just not clear on how, as you showed in these observations, we always see these sort of filaments, coherent pathways, as you said, down into the interior. I sort of see how the submesoscale overturning circulation might inject fluid below the mixed layer, but then many of those overturning circulations should close near the mixed layer base. So what is sort of doing the coherent transport much deeper than the mixed layer?
Yeah, so I want to say that closing the secondary circulation doesn't happen in the same plane, right? So we always see these secondary circulation figures which are like in one plane, but the flow is going out of that plane much faster. And the secondary circulation is closed much further downstream. So you have to think about the closure of the secondary circulation in Lagrangian frame. That water parcel that went down is no longer going to come up in the same place at the front. It's gone much down front before it comes up somewhere else. So that's one comment I wanted to make. And then the other part is you're saying, what about the closure? What happens when it goes below the mixed layer, right? And I think that these pathways that are crossing the base of the mixed layer are along these sloping isopycnal pathways. So I know that, people have looked at mixed layer restratification and Baylor's parameterization, Baylor-Fox-Kemper as a parameterization that looks at the overturning in the mixed layer. We have a student, Amit's student, Yuri, just did some simulations in which he tried to look at how things are fluxed across the base of the mixed layer. And so that pathway is very leaky. It is getting things across the pathway of the mixed layer, which is not accounted for in the mixed layer eddy restratifying parameterization, which has the, if you're thinking about the overturning circulation, it's only within the mixed layer, whereas the eddies are doing some things across the base of the mixed layer. There's also a barotropization that occurs of these eddies. So if I start with a simulation which the isopycnals are flat at the base of the mixed layer and the fronts are only in the mixed layer, then after some time, I see the isopycnals below the mixed layer also become sloping and connect with the fronts in the mixed layer. So there's the connection of the mixed layer fronts with the subsurface pycnocline. And you might say, how deep is that going? And the sort of the quick answer I can give you, it's going as deep as those isopycnals are tilted, as deep as you can find sloping isopycnals. We have a paper that was done by a postdoc of Amit Sanjeev Ramachandran, which looks at how deep those circulations are, the secondary circulations. And we can look at fronts which are shallow, confined to the mixed layer, and fronts which have isopycnals that slope deeper into the pycnocline.
Thanks. I'll look that paper up. Thanks.
Okay.
Other questions? I did want to ask about sort of the practical questions we think about when we think about capabilities from space. And those include two things. One is, of course, we can only see the surface from a satellite. And so we've had an ongoing question about when we think about vertical velocity, how much we can really know if we're only seeing the surface velocity. So you've showed the surface vorticity is a really useful diagnostic, but do you think that's enough? Or are we missing something that has to be filled in with models?
Yeah, so I don't know the exact answer to your question, but maybe I can show you a slide where we have tried, thinking about how you might use surface data. So this is done by my student Jing He, and we tried to calculate the vertical velocity. So this was the flow field is an upwelling front. It's like this. We're blowing wind in one direction, and I have a wall on my right side, which you can think of as the coast. And we create fronts of different strength by varying the wind and the stratification. And these are sort of many model simulations, different, an ensemble of model simulations that we have. We're looking at the vorticity. So now we try to say, how can we infer the vertical velocity from surface data? And our true vertical velocity field shown on the right is our model simulation. And then we try different methods. So the first is that we take surface divergence of the field and we integrate it downwards. So we're only using surface data. Okay, so surface divergence integrated actually does a reasonably good job near the surface. But since you're just integrating dWdz, you need to know where dWdz changes sign or what's happening. So obviously it gets really bad as you go deeper. Okay. Then we used SQG, so surface geostrophic methods, and we use ISQG, which has the interior modes. This was done by Jinbo Wang. And we use that method, and that helps you identify some of this, but really doesn't give you the strong asymmetry. And we use linear regression. So you're saying like, yes, we know where the fronts are, and so we know where the positive and negative vorticity is. Actually doesn't do too badly. And then we use some machine learning methods, so random forest and CNN. So what was really interesting is that all these methods, random forest, even the linear regression is not bad. Like we can say, oh, we know where the fronts are. We know that positive vorticity is where we see downwelling, and the answer is not bad. But when we add some noise to the data, then the only method that does reasonably well is CNN, the convolution neural net. And I think it kind of filters out the noise in some way, so that even when we make the surface fields noisy, 10% noise, then the CNN network, whether it's the convolution neural net for large vertical velocities, medium and weak, it does a reasonable job of reconstructing them. But none of these methods do a good job in the interior, very deep. So they're good in the upper surface layer, maybe going a little below the mixed layer, but not very deep. So yeah, there's some hope. Maybe, but that's, none of us like to just use machine learning as a black box, as you know. So I want to say there's hope, but yeah.
Well,
but there's also the noise factor. Yeah.
Yeah.
And then we tried other things like coarser resolution. Like what if we have 15-kilometer resolution from SWAT?
That was my next question. So perfect.
Yeah, I don't have the figure in my slide deck, but we tried coarsening the resolution. I can send it to you. Yeah.
yeah, I think sometimes what we think we can get from the altitude of a satellite orbiting the Earth is once enough averaging is done to beat down the worst of the noise is sort of 15-kilometer resolution. And you've made a case that the difference between 4 kilometers and 1 kilometer is really big. So if you go another factor of 4 coarser to 15 or 16, are you losing too much of the tails?
True, but what we do have is we have SST, or if you know that you have surface densities at high resolution, then you can use some of these data, like machine learning methods to use high resolution SST and coarser resolution velocities. So you get quite a lot of gain in that way by combining those. There's also, I want to say, like, because you're thinking about WACM, there's one big difference between WACM and SWOT, if I understand this correctly, please correct me if I'm wrong, is that WACM will give you the fields with the divergence, whereas SWOT, you are using surface pressure. So in the end, it's a geostrophically balanced non-divergent field. Is that correct?
Yeah, I think the easy way to think is one is geostrophic velocity and the other is total velocity.
Yeah.
And
so I think
much
that
of the
there's more
sub-mesoscale
hope,
motion is tied up in.
Yes. So from that standpoint, I really like the total velocity model.
Yeah. So other questions for Amala? Amit has one in the chat.
Sorry, I didn't mean to monopolize the questions, Amala. So if other people
it's
have
purely,
more
CNN
important
was the
questions.
purely machine learning. Yeah.
So is there, because I mean, we have all this beautiful machinery from the surface quasi-geostrophic stuff, some of your work with Joe Lacasse and then Patrick Klein's work and so on. It'd be a shame to completely throw it away and then only use some purely machine learning algorithm, which may tune differently in different parts of the world. So,
So I agree with you. I agree with you, especially for the interior, because I think one important thing that we've been thinking of is what is the vertical structure of the vertical velocity, and that we don't seem to get very well from these machine learning methods that use just the surface. But we have some idea of the vertical structure of the ocean from, the vertical modes we can think of, or the surface QG modes. And so I think we could do, agree.
Thank you.
So in that vein, one of the arguments has been that data assimilation 4D VAR is a form of machine learning and might be able to provide the way to build the physics into the machine learning. Is that a possibility?
Yeah.
Maybe Bruce will comment.
Well, it's my information content is low because I'm going to say it, right? But I think it'd be very interesting to try it, right? To try an assimilation on that data set, right? And see what happens, right? Because, what is 4D VAR, right? But least squares plus model dynamics, right? It's all it is. It's just regression with the dynamics. So, it would be wonderful to see it in that spectrum, right? Try it on the same problem, see what it does, right? Anyway, yeah, thanks for the question. Or thanks for the great seminar, Amala. That was really very clear and nice. And that last part is very interesting. So thank you, Sarah.
Thank you, Bruce.
Okay.
Thank you.
Yeah, are there any other questions?
Amala, maybe you answered this or said this when you answered Jacob, but what depths were those vertical velocity and vorticity statistics from relative to your stratification or?
The statistics that I showed in that this very skew statistics are really in the mixed layer, right? So when you go below the mixed layer, then you lose the skewness in the vertical velocity field and the vorticity field. And so as you go deeper.
And what about the uplift versus isopycnal vertical velocity? That must be in somewhat stratified water. Yeah,
so we looked at that below the mixed layer. And we were thinking of so we did that decomposition and an isopycnal at a depth of about 75 meters. So we wanted to be in the light layer, but the mixed layer was shallower. So it was in the stratified pycnocline. I think it was like 80 meters or so. So there was light, so the nutrients were consumed on that surface, but it was in the pycnocline because we are thinking of like subtropical gyres. You know.
Okay.
And obviously you can't do it in the mixed layer because it's.
I'm not sure I totally understood Amit's comments and question at the beginning, but going way back, Dave Chapman and I did a calculation back in '95 where you could pretty clearly see the potential vorticity tongue getting sucked underneath a mixed layer front in that unstable situation. I'm sure that other people must have done that also since then in much more complicated settings. So
yeah, so was that high or low PV? Because I think Amit is referring to low PV water being subducted. What we're seeing a lot of is high PV water, right? Positive vorticity. And so there's, I think there's some confusion in the, I don't know if it's confusion, but I think there's people have seen observations of low PV boluses subsurface, which come from the surface. And there's been a few papers on that. Here, what we are showing is it's the high PV water, which has got high positive vorticity, which is being subducted. And I feel like we need to kind of, we need to kind of resolve what we mean.
I can't remember, honestly. One part of it was black and one was white. It was grayscale contours back then. Thanks. Nice seminar, really interesting.
Thank you. Thank you.
Yeah, well, this was great. Thank you very much. Another round of applause for Amala.
Thank you. Seminar. Thank you very much. Thanks, everyone. Thank you, everyone. Thanks. Thank you. All right, I'm going to log off. Thanks.
Yeah, thank you so much.
Thank you very much. Yeah, thank you.
Really great seminar. Bye.